Pluto is a far-off and dazzling planet that was once essential for our nearby planetary systems family. However, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggest that this freezing world is on a possible brief trajectory with Neptune. But how could this happen, and what might be the consequences of such a huge event? Are we seeing a looming crash, or is there something else about this approaching gigantic mishap? Join us as we investigate the potential results of a Pluto-Neptune influence. Pluto, a former planet that was renamed as a dwarf planet partly due to its eccentric orbit, remains a subject of interest and study in the vast cosmos, as shown by recent conjectures by leading experts. Pluto's orbit is dangerously close to Neptune's, and astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential catastrophic impact between these two planets that could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our nearby solar system. It takes a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its unusually elongated shape, differing greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is that it's tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to other planets. This tilt and anomaly add layers of complexity to its orbital pattern. Perhaps one of the most captivating aspects of Pluto's orbit is its alignment with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging our expectations about their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its peculiar orbit. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's path stood out with its steep tilt and irregular shape. The mystery grew with the realization that Pluto's orbit actually crosses Neptune's. The complexity of Pluto's orbit amid these intricacies is evidence of the complexities of celestial mechanics. The three-body problem in space is all about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem demonstrates how its orbit, Neptune's path, and the Sun's gravity all work together in a complex manner. The terms alpha libration and degree libration, along with the VZK influence, are crucial to this conundrum. According to astrophysicists, what's keeping all planets in their orbits is a phenomenon called alpha libration. As for Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned around 90 degrees away from Neptune. This spatial separation is key in preventing their orbits from affecting each other. Expansion libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned well above their orbital plane, providing an extra layer of protection from potential collisions. Another critical factor in this situation is the VZK influence, named after three researchers, Zippel, Leo, and Kai, who studied how objects move in space. It's about how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull affects how they move. For Pluto, the VZK influence helps explain why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming chaotic, this influence helps keep it moving smoothly. The VZK influence shows that although things in space might appear wild and erratic, certain patterns and laws maintain control. These forces help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or lose its course. The three-body problem helps us understand how these orbits change based on how these celestial objects pull on one another. Focusing on this helps us learn more about Pluto, our solar system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, Despite these stabilizing factors, Pluto's orbit is still relatively turbulent, with minor changes in initial conditions leading to huge differences over millions of years. However, these peculiar properties of Pluto's orbit have been shown to maintain stability over especially long timescales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where for every orbit Pluto completes around the Sun, Neptune completes 3. This connection helps keep Pluto's orbit stable. However, Neptune is not alone in this. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn contributes substantially too. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady orbit for a long time, even billions of years. It appears that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These phenomena are crucial when it comes to the universe, as they maintain the stability and consistency of celestial bodies' movements. Without these forces, the solar system would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, causing a ripple effect on other celestial bodies. For Pluto, especially with discussions about it potentially crashing into Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the dynamics of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of stability through the intricate exchange of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our position in the cosmos. Exploring the depths of space often forces us to confront the odd nature of celestial bodies, and Pluto's orbit is a prime example of this phenomenon. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can dramatically alter its long-term path. Direction in the endlessness of our planetary group, Pluto possesses a one-of-a-kind spot that challenges how we might interpret planetary grouping and elements. Since its discovery in 1930, Pluto has gone through broad review, prompting huge discoveries about its design and conduct. One of the most interesting parts of Pluto is its surface, which is a mind-boggling embroidery of ice, rock, and different mixtures. The New Horizons mission, which flew by Pluto in July 2015, gave striking information about this far-off world. The outer layer of Pluto is described by immense fields, transcending mountains and deep valleys. One of the most beautiful highlights is the Sputnik planum, an enormous heart-shaped plain primarily made out of nitrogen ice. This region showcases an assorted cluster of landforms, including huge ice racks and what seem to be flowing ice sheets. The presence of these elements suggests that Pluto might still be geographically dynamic, regardless of its significant stretch from the Sun and low temperatures. One more enrapturing part of Pluto is its air, basically comprised of nitrogen, with hints of methane and carbon monoxide. Pluto's air is slender, yet shows charming occasional varieties. As Pluto moves toward the Sun in its extended orbit, its air can grow and get. This powerful way of behaving is an impression of the perplexing connection between Pluto and its environment. During its closest approach to the Sun, a portion of the air gases might freeze out onto the surface, while as it moves farther away, these gases can sublimate once again into the air. The collaboration between Pluto and its largest moon, Charon, also adds intricacy to the system. Charon is relatively large compared to Pluto, with a diameter about a portion of that of Pluto itself. This size ratio means that the two bodies are in a common orbit around a point in space that lies between them, as opposed to Pluto just spinning around Charon. This unique relationship adds to the complex gravitational elements in the region, influencing the orbits of other objects in the Kuiper belt. The Kuiper belt, a region beyond Neptune populated with little frosty bodies, is home to various other dwarf planets and potential impactors. This belt is a supply of old material from the early solar system, giving researchers a brief look into its development. Pluto's orbital qualities might give bits of insight into the development patterns of these far-off objects, suggesting that interactions with larger planets might have played a critical role in shaping their current orbits. One of the key implications of understanding Pluto's orbital elements is the potential effect on how we might interpret the solar system's evolution. Gravitational interactions from adjoining giant planets like Jupiter and Neptune can modify the trajectories of smaller bodies, including those in the Kuiper belt. Such associations can lead to changes in orbits, potentially resulting in collisions or ejections from the solar system. As researchers continue to investigate the details of these interactions, they might uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical issues about classification in astronomy. The decision to rename Pluto as a dwarf planet in 2006 was controversial, starting conversations about being an all-in-all. Pluto's orbital relationship with Neptune and its position in the solar system act as powerful reminders of the complexity of the universe. Through continued investigation, we can expand how we might interpret these faraway worlds and the forces that govern their movement. Continuing our exploration of Pluto's fascinating orbital elements, it's essential to recognize how the gravitational forces applied by distant planets shape the behavior of objects in the outer solar system. While Pluto's orbit might seem tumultuous at first glance, it is precisely these complex interactions that allow it to maintain stability despite the apparent chaos. As we delve deeper into the mechanics of Pluto's orbit, we uncover more layers of intricacy, revealing insights into the powerful cycles that govern the movement of celestial bodies. One captivating aspect of Pluto's relationship with Neptune is the long-term stability of their orbits, despite their occasional proximity. This is due to an exceptional resonance between the two bodies known as a 3:2 orbital resonance. For every 3 orbits Pluto completes around the Sun, Neptune completes 2. This resonance keeps Pluto and Neptune in a steady arrangement, preventing them from colliding, despite their orbits crossing. The stability provided by this resonance is a beautiful example of how gravitational interactions can ensure the precise movement of celestial objects. This 3:2 resonance is a result of the gravitational back and forth between Pluto and Neptune. Each time Pluto and Neptune approach each other in their orbits, their gravitational fields interact in a way that ensures their paths stay synchronized over extended periods. The result is a system where, even as Pluto crosses into Neptune's orbit, the two bodies are always carefully separated by the constant resonance. Thus, the probability of a collision is virtually non-existent. Further investigation of the Kuiper belt, where Pluto resides, reveals that Pluto isn't alone in this unique orbital relationship. Many other objects in the Kuiper belt also exhibit gravitational interactions with Neptune, resulting in similar orbital resonances. These objects are often referred to as Plutinos because their orbits are similarly locked into a 3:2 resonance with Neptune. This large group of icy bodies further highlights the importance of Neptune's gravitational influence in shaping the structure and stability of the outer solar system. In addition to gravitational resonances, the process of planetary migration likely played a key role in shaping Pluto's current orbit. Planetary migration refers to the slow movement of planets over millions of years, caused by interactions with the protoplanetary disk or other bodies in the early solar system. During the formation of the solar system, giant planets like Jupiter, Saturn, and Neptune are believed to have undergone migration, shifting their positions and altering the orbits of smaller bodies in the process. This migration may have influenced Pluto's orbit, nudging it into its current irregular and tilted path. The migration of Neptune, in particular, is thought to have played a crucial role in the current configuration of the Kuiper belt. As Neptune moved outward from the Sun, it likely cleared space for other bodies, including Pluto, to move into their current orbits. This dynamic process helped shape the distribution of icy bodies in the outer solar system, leaving behind the diverse array of objects we observe today. Another aspect of Pluto's orbit that deserves attention is its occasional intersection of the orbital paths of other objects in the Kuiper belt. While the likelihood of a collision is very low due to the stability of the resonance with Neptune, the potential for gravitational interactions with other objects in the belt remains a possibility. These interactions could cause slight changes in Pluto's orbit over time, leading to minor variations in its path. However, given the long timescales involved, these changes are likely to be gradual rather than catastrophic. Despite its relatively small size and distance from the Sun, Pluto continues to offer valuable insights into the workings of our solar system. Its unique orbital characteristics, including its interaction with Neptune, highlight the complexity and interconnectedness of the forces that govern the movement of celestial bodies. The study of Pluto and its orbit has implications not only for understanding the dynamics of our solar system but also for exploring the broader patterns of planetary motion that may exist throughout the universe. As we continue to study Pluto, we are reminded of the vastness and mystery of the universe. Although Pluto may no longer be classified as a full-fledged planet, its place in our solar system remains an essential piece of the puzzle in understanding the evolution of planetary systems. By continuing to explore these distant realms of space, we can gain a deeper appreciation for the forces that shape the universe and our place within it. The ongoing study of Pluto and other Kuiper Belt objects promises to yield new discoveries that will continue to challenge and expand our understanding of the universe.